Actually, you can think about this as like, this is the way you do any sort of fabrication at the micron and nanoscale, right? So whether it's electronics or photonics, it's all doing very similar things. So the way it generally starts is you'll start with a silicon wafer. So silicon wafer, silicon's a really nice material. We can make them grow in nice single crystals, cut them into nice wafers, so they're like big flat surfaces essentially that you can do anything you want on.
All electronics is based on that anyway.
Right, so it also has to be a nice semiconductor with very nice materials properties for electronics. Yeah, so we start with a silicon wafer. And what will then happen first is we need to grow what we call the undercladding. Right, so we're gonna add a layer on top of the silicon, which will be silicon dioxide. So silicon dioxide, in our case, happens to be it's a relatively low refractive index material that's also very easy to deposit on silicon. And then what we'll do is we will then deposit our core material for our waveguides. So in this case, it has to be a chalcogenide glass. So we'll deposit another layer on here. This is our chalcogenide glass. I should add thicknesses here. So this is 3 microns in thickness, and this is 1 micron in thickness. So the chalcogenide glass has an index refraction of around 2.1, so the silicon will have an index of 3.45. And for all waveguiding purposes, the easiest way to think about it is light likes to travel in high index materials. So if we had put the chalcogenide glass directly on the silicon, light would preferentially travel into silicon, and we wouldn't have any sort of guiding behavior with our chalcogenide glass. Silicon dioxide happens to have an index of 1.45-ish.
Yeah.
So it's a relatively low index material. So what we're doing is we're isolating our chalcogenide glass from the silicon wafer itself with the silicon dioxide. We can compare to fibers. So if we have a fiber, right, we've got generally a fiber has a core and then a cladding, and it has a very similar idea, right? So your cladding is maybe it's like undoped silicon dioxide, or maybe it's plastic. This will have a relatively low index, right? So the fiber, the cladding, yeah, index of 1.45, and then the core will have an index of 1.47. So every single time when you have any sort of guided light, you always want a higher index material surrounded by a lower index material, because that's the way that way when you have light in here, it'll preferentially travel more in the high index material. So this basic structure is going to be something that we essentially will try to replicate on a silicon wafer, with obviously different geometric. It won't be a circle, it'll be rectangles this time, but otherwise the basic concept is all there. So for something like this, again, we can use techniques that are used for the electronics industry, where they fabricate like thousands of chips on one single wafer at the same time. So it's like a massively parallel process. It gets much cheaper. The next step would actually be to deposit a resist on top of it, which is actually another planar layer. So you put another, and this is resist. So the resist itself, it can be any number of possible chemicals. It can be almost any number of possible thicknesses. You choose it based on how you optimize the process afterward. Typically a polymer.
Polymer.
Yeah. There's only a few glasses, and those are all electron beam resists. So the next step after this is if we're going to do photolithography, which I think is the easiest to sort of think about, and also the one that you would use for mass manufacturing, right? So like electron beam lithography, again, as Sam mentioned, it's really expensive because you have to like actually write every pixel. So it's a very serial process, therefore very expensive to do large areas. For photolithography, you can expose an entire wafer in one shot with like a single exposure of light. So that's generally the way that it's done for mass manufacturing. So for photolithography, what you do is then you put a mask on top of your resist. So what that means is like it covers certain areas. So let's say our mask is here, and those are chrome. It's usually the mask is chrome on quartz.
On quartz.
So the chrome obviously blocks UV light. The quartz lets UV light through. So we have the mask on top of there, and then we expose it to UV light. So then you have light coming in right here. Oops, that was terribly drawn. It's fine. Right, so you've got light, but obviously the areas where you have the mask, the chrome, it gets blocked, and all you expose is here. Right, so you expose these areas of the resist. So you expose those areas of the resist. Now, the resist can be one of two different types of resist. It can either be a positive photoresist, in which case what happens is the areas that are exposed, you break up a polymer so it becomes easier to dissolve. So when you then put this into a special developer chemical, it'll selectively dissolve the areas that were exposed to light. So that's a positive resist. And the way to think about that is that what remains should be a positive image of your chrome. Right? So if you think about in terms of photography, it's a positive image to match your chrome mask. It could also be a negative resist, which is the exact opposite. So whatever is exposed to light helps polymerize certain areas and makes it harder to dissolve, which means that when you dip it in your chemical developer, the areas that aren't exposed to light get dissolved away, and you end up with a negative image compared to your chrome. Right? So let's just say in this case we have a positive resist. So I'm going to redraw everything so that we can start somewhere here right now. Again, this is our silicon. This is our silicon dioxide. This is our tricotinite glass. And now what we have in terms of the resist is something like this, right? So we have some resist here, some resist here. Right. So we've exposed it to light, we've dipped it in our developer chemical. It's a positive resist, so all of the things that have been exposed to light are dissolved away, and this is what we have left. And now what we're going to do is something called an etch. So the way an etch works is generally you want your etch to be perfectly anisotropic, so you want it to be straight down only. And what that allows you to do then, right, is, do I have more colors? Not really. So the etch, you will use some sort of gas, and usually it's like a plasma, so you can use electricity to drive your atoms straight down, so you can like make it more directional. Well, it attacks everything, right? But obviously, everything that's protected by, that has resist on it, it doesn't etch very quickly. And wherever there's exposed tricotinite glass, you will etch it down. So you end up getting something like this, where this all sort of disappears. And this all disappears. And this all disappears. Right? So what the etch then does, right, is it transfers the pattern from the resist that you developed into your material that you care about. And now that means that, and then after you're done with the etch, you'll remove the resist chemical. Usually that just means you can either sometimes dissolve it in certain chemicals, or you can use a plasma asher to clean it. Essentially you take oxygen and you burn all of the resist, because generally it's a polymer, so it's organic chemicals that you can pretty easily burn off. And that means what you're left with is, again, I'll try to redraw the necessary. So here's your silicon, here's silicon dioxide, and now what you have left is this, where these are now tricotinite glass. Oops, tricotinite glass. And we're almost to the finished waveguide structure, actually. So the last part now, so you've got your pattern tricotinite glass, and actually you could use this as a waveguide already. You just have an air cladding on top, right? But what we'd probably do for at least part of the chip, so we want to, so obviously if for anything that we need exposed to the methane, we have to keep it like this, because we need our methane to be able to interact with the light, which is going to be sitting in this waveguide, so we need the methane right next to the waveguide. But for any areas where we don't need the interaction, let's say, the coupling area, or maybe we have a different part of the circuit. Maybe it's our reference waveguide that we have that we don't want interacting with the methane. We can cover it again with we can deposit another silicon dioxide layer on top and cover it, right? We can cover it with SiO2 if we want. Right. So what this means for like top views, so these are all side views, right? Side views. Oops. Here. But the top view will look something like this. So if you've got a chip here, the top view will look something like this. So maybe you'll have, I'll just draw two different waveguides. So maybe you'll have one waveguide here, right, going from one end to the other, and you'll have another waveguide here. So like this view is like a cross section, right? So maybe it's like a cross section here, right? This is our tricogenide glass, right? And then the last little thing that we have is our silicon dioxide. So we like open up a window, and all of this, the rest of the area, is all covered by an upper layer of silicon dioxide. Right.
So you're saying that you just make a hole in the silicon dioxide, which exposes one waveguide to methane
methane,
gas.
right.
And everything else is sealed and covered nicely and protected from methane.